Bonjour, good morning, everyone. Of course, I want to start this talk by thanking the organizers for letting me the opportunity to be here and say happy birthday to Professor Kefelec. I must say that this is the first time I'm attending a meeting in the honor of some professor to celebrate his birthday, and I'm getting the present myself. This is because it has been a long time since I worked on composition operators, and well, coming to this meeting has been the excuse to go back to some of the problems I was not able to solve during my PhD a long time ago. So this means that, well, as you can see, I'm going to talk about a joint work in progress with Dragan Vukotic from the Universidad Autónoma de Madrid. And, well, I would like to give you the theorem, but unfortunately, I cannot solve what I want to solve. Though I thought that since there are as many experts in this room on composition operators, it could be a good excuse to get some suggestion, which of course, any comment or suggestions are most welcome. But just in case, I thought that perhaps, well, this could be a topic that would be of some interest for you, and in particular for Professor Kefelec. I took a look at the list of publications you have. It's impressive. Thank you very much, not only for being such a nice person, the chances I had to talk to you, this is what you showed me, but also such a nice mathematician, such a good mathematician, and for all the things I have learned from your papers. So here I go. Let's start. Let's see if I am able to do this properly. Well, as I said, I'm going to talk about a problem I cannot solve, and indeed I would say that the talk is going to be almost expository talk. The proofs I'm going to show you are quite easy, so probably all of you will be able to follow the arguments, I'm sure about that. But let me start from the beginning, something that we all know the second day of the talk. So here we have a composition operator with symbol phi, which is a self-map of the unit disk. So let's see. That is a holomorphic functions whose range is contained again in the unit disk. So this is going to induce a composition operator which acts on the space of holomorphic functions in the way it is written here. And I would say that everyone who works on composition operators wishes to relate the operator theoretic properties of the operator with the operator with the function theoretic properties of the symbol. Our last speaker yesterday showed us several examples, such as a composition operator, is compact on the Bergman spaces if and only if, well, the angular derivative of the symbol satisfies certain conditions. So, of course, this is the sort of main goal. With this in our hands, I will more concretely be interested in the norms of composition operators, okay? I know that several people in this room have worked on this problem in several different spaces. I tried to make a list, but in order not to make any mistake, please let me just focus on this example on the Hattie space, which is defined as, you know, as the set of holomorphic functions in D such that, well, the integral means over the circle of radius R are square integrable. So this soup of these integrals are uniformly bounded, and well, you also know that every function in this space has a radial boundary limit that I am again denoting by F, and well, these three identities hold, and whenever any of them is finite, we say that our function belongs in the Hattie space H2, And moreover, these quantities are the square of the norm of f. Well, it's a direct consequence of the Littlewood famous subordination theorem that whenever you have a symbol that fixes the origin, then the composition operator is going to be bounded in H2. And indeed, it's not difficult also to compute, the norm of a composition operator induced by this nice involutive automorphism of the unit disks. You can control the norm. Indeed, the estimate for the norm was obtained by Reeve, and he was Nordgren, the one who proved that the norm of such composition operator is exactly equal to this quantity. So the norm depends on the value of the symbol at the origin. Of course, whenever the symbol fixes the origin, well, since we are lucky and the function 1 is in our space, then obviously, as a consequence of the Littlewood subordination theorem and this easy fact that I just mentioned, we have that the norm is equal to 1. So this gives us this estimate for the norm of any composition operator on this Hardy space. Well, and here I wrote just a line for the proof. So if you can control what happens with the norm of composition operators induced by a symbol that fixes the origin, and you can control the norm of the composition operators induced by this automorphism of the unit disk, then you can control the norm of any symbol in the space. Okay, what about the exact norms? This one. This is the bigger one, and it is difficult to me. Well, as I just mentioned, as long as the symbol fixes the origin, then the norm is equal to 1. And whenever the symbol is an inner function, then you have this equality here. This was obtained by Nordgren in the 60s, okay? Well, the other example I know in relation to the exact value of the norm of a composition operator in the Hardy space is, well, this one in relation to these affine symbols. This was proved by Cowen using the tools from the Hilbert space. And I would say that that's all. I hope I'm not forgetting anything. Please correct me if I am saying something incorrect, but I would say that that's all so far, okay? By the way, it is also known that the isometries, I did not write this on the screen, but it is known, and all of you know that isometries among the composition operators in the Hardy space are those operators induced by inner functions that fixes the origin. Okay, I will be back to this later. Well, while preparing this talk, I thought, well, before going to the space, I'm going to consider in this talk. But, well, the title is sort of clear. So I'm going to talk about the composition operators on the Bloch space. But before introducing, introducing the space, I'd like to say a few things on some sort of auxiliary results. I have to thank Artur because yesterday he made half of my job. So, well, just in case, let me recall you that given any 2 points in the unit disk, Z and W, well, this is precisely the value of the pseudo-hyperbolic distance between these 2 points. So this is essentially the value of the automorphism I wrote before, sigma W at the point Z. Artur mentioned yesterday, and you will know that, well, it is a direct consequence of the Schwarzschild lemma that this metric is contractive in this sense. So the pseudo-hyperbolic metric between the images of 2 points by a self-map of the unit disk is always less than or equal to the distance, pseudo-hyperbolic distance, of the original points. This metric has a very nice property, unless my point of view. So if one of the points is equal to 0, then the pseudo-hyperbolic distance coincides with the Euclidean distance. And, I forgot to say that here, whenever phi is an automorphism of the unit disk, again, by the Schwarzschild lemma, we have an equality here. So automorphisms of the unit disk are isometries with respect to this metric. And of course, you all know that if for 2 different values, W and Z, we have equality here, then we have equality everywhere, and we again deal with automorphisms of the unit disk. So if we consider a pseudo-hyperbolic disk centered at the origin, which is due to this identity here, an Euclidean disk, and we apply an automorphism to this disk, being every automorphism of the unit disk a Mobius transformation, we get another disk. Another disk that is going to be the pseudo-hyperbolic disk of centered A, if I consider just this sigma A, and pseudo-hyperbolic radius R. This is, again, an Euclidean disk, as I was trying to explain, and you can compute the pseudo-hyperbolic radius in terms of the center, Euclidean center and Euclidean radius of this disk. Here is the formula, and perhaps some of you can recognize that formula here, right? So as long as we have a strict inequality here, so the image of the disk under this function is compactly contained in D, then we have that the norm has a geometric meaning. This is the Euclidean radius over the pseudo-hyperbolic radius. Okay? Well, I would say that this is the only disadvantage I find to this metric here. For any 3 different points in the unit disk, this inequality, strict inequality holds. So somehow this metric is not additive in geodesics, okay? But we still have some chance to fix this question by just considering the hyperbolic distance in the unit disk, which is, as you know, given by this formula, which is nothing else than the infimum over all regular curves that join the point Z and W in the unit disk of this integral I wrote here. Again, this is a metric, since the function 1 over 2, the logarithm of 1 plus x over 1 minus x is strictly increasing. We can show just by the hereditary question we get from the pseudo-hyperbolic metric that this inequality holds for any analytic self-map of the unit disk. And we have equality here at 2. Oh, this is, sorry. Well, I hope you can follow me. Equality here for 2 different points if and only if phi is an automorphism of the unit disk. And moreover, I'm sure we all made this problem when we were young. Well, if I want to control the geodesics in this metric, these are the diameters passing through 0, of course, and also circles that cut the boundary of the unit disk in a straight whoops, sorry. Well, this angle is pi over 2. And in this case, I was trying to explain before, we can say that whenever I take 3 points on a geodesic in this order, so here is W, here is Y, and here is Z, then the pseudo-hyperbolic distance satisfies this additive property on geodesics, okay? Well, hopefully this will help me somehow, though perhaps later. Well, with this hyperbolic metric at hand, I can consider the ratio of the hyperbolic metric between the points phi of W and phi of Z, then over this distance between W and C, and take the limit as W tends to C. That's, I mean, in this case, I obtained what I will call the hyperbolic derivative of phi at the point Z, and it is equal to this quantity here that we have already seen before. Of course, let me use this symbol to denote the supremum over the points in the unit disk of the modulus of these hyperbolic derivatives. And again, the Schwarzschild lemma tells us that, well, this is always bounded by 1. If for some point we have an equality, then we have an automorphism of the unit disk. But as we will see, there are plenty of functions satisfying that the supremum of the modulus of the hyperbolic derivative is 1, and they are not automorphisms. Okay, I will go back to this later, but I will also justify why I'm interested in telling you these properties on the hyperbolic derivatives. Well, some other properties it has is that it satisfies the chain rule. Here it is, the formula for that. So that notice that the supremum of the hyperbolic derivative of an automorphism is going to be controlled by the supremum of these two functions. Being both of them less than or equal to 1, I can control this supremum. And of course, there is a sort of subordination property. So whenever I have two symbols, phi and psi, and the bigger one, let me use this expression, the bigger one in this sense, so phi of d is contained in psi of d, then if I have an univalent, that is a conformal mapping psi here, then the supremum, the norm of the hyperbolic derivative, if you allow me to use this terminology, is controlled by the other one, okay? Well, some examples. I guess that here I have some examples. What does this norm of the hyperbolic derivative tell us? What does it tell us? Oh my God. Well, it's not difficult to check that whenever you have an affine mapping of this form, and assume first that, well, it maps the unit disk onto a disk that is contained compactly in D. So I will write this in this way. Well, sorry, my pictures are not very, well, I think this is understandable. So I mentioned before that these Euclidean disks are also pseudo-hyperbolic disks, and therefore I can compute the pseudo-hyperbolic radius, and it is a question of making some calculations to check that the supremum of the modulus of the hyperbolic derivative coincides precisely with this pseudo-hyperbolic radius. So this would be the case when the modulus of A plus the modulus of B, yes, I wrote it correctly, is less than 1. And if this quantity is equal to 1, so this means that the disk is going to be tangent to the boundary of the unit circle. So if I agree with the, I would say this is something we all would agree that the pseudo-hyperbolic radius of this tangent disk horocycle, oh, so I cannot point then in a digital way. The pseudo-hyperbolic radius of these disks are equal to 1, then in either case, we have that the supremum of the hyperbolic derivative is equal to this pseudo-hyperbolic radius. Regarding Mobius transformations, we can also compute this supremum very easily, because it is easy to show that any such transformation can be written within these terms. And since the hyperbolic metric is invariant under composition with Mobius transformations, I can reduce my problem to the previous one, and again, I have exactly the same result. This condition here is, well, just to guarantee that my function phi maps the unit disk into itself, okay? And of course, this other one, as you know, is to avoid that the function is not constant. More examples. Functions with angular derivatives. So due to the Julia-Carathéodory lemma, you know that the condition I'm writing here means that my function phi satisfies the following two conditions. Well, I don't know if I mentioned that any function in the Hardy space has radial limits almost everywhere, okay? And H infinity is contained in the Hardy space, and every self-map is in H infinity. So, well, if I assume that this condition holds, this means that my function phi has radial limits at this zeta, and the modulus of this radial limit is equal to 1. But also it means that the derivative has angular limit at the point z whenever this limit is finite. Well, in this case, we all know that if an angular derivative holds at the point zeta, well, this could be phi of zeta, then here I have a tangential approach, okay? And well, in these cases, we can show that the supremum of the hyperbolic derivative in modulus over the unit disk is the limit, the radial limit, as we approach to that point, and indeed, this value is equal to 1. So these are examples of functions that are not necessarily automorphisms of the unit disk, but they have a norm. The norm of the hyperbolic derivative is equal to 1. And some other examples that are not included here are provided by the so-called lens maps. So notice how beautiful, at least to me, these functions are. So we take the unit disk, and this function P maps D onto this right half plane. Then we apply a power to get a sector, and then we go back to the unit disk by using the inverse of this Mobius transformation. And therefore, what we get is a sort of lens-shaped domain that looks like this. So here I have an angle alpha pi. So these are functions. The range is symmetric with respect to the real axis, and here is what we have. You can compute exactly what the value of the hyperbolic derivative at a point z is. I stated this result in the same terms as the authors Osokawa and Ono used in their paper proving this result. So they say, just take a point W here, but as you all can see, since I am using a Mobius transformation, this half line comes from a circle passing through -1 and 1, and this angle here is precisely this one, so that if I take a point Z in the disk on this pink arc of the circle, the value of the hyperbolic derivative of the length map is just given by the parameter alpha that defines the transformation, and precisely this angle T. Okay, I wrote theta maybe, well, T. And of course, since multiplying by a positive number alpha less than 1, well, the cosine in the denominator is bigger than the cosine in the numerator, then you get that the supremum is exactly equal to alpha, and indeed, for all the points on the real diameter, you have that this value here is precisely the maximum of the hyperbolic derivative, okay? Well, this is going to be sort of interesting for us. And well, just to show you some of my theorems, I decided to include this here. This is just a particular case of this more general one. So what I wrote in the upper part is a classical definition due to Lindelof on what is a corner of opening alpha. So let me assume that the mappings I'm considering here are smooth enough. Maybe here I can write. So I have a function phi, and this is going to map the unit disk onto a Jordan domain, again contained in the unit disk, so something like this. Well, I decided that I have a sort of particular situation that one of the boundary points, after applying a rotation, I will consider this is the point 1, goes to the point 1 without loss of generality. And the thing is that here is what happens. When I approach the point 1 from the upper part of the circle, then I get a curve that approaches somehow to this point 1 with some angle beta. So I'm going to consider this determination of the argument. So I approach there to this angle beta. And then this other side of the circle goes to some other limit, which is this beta plus alpha pi. So this is the condition that, well, gives the function phi, or rather the function, the point phi of 1 to say that it has a corner of opening pi alpha. Well, it happens that whenever I have such a nice function, so it has to be univalent and map the unit disk onto a Jordan domain contained in the disk, whenever I have a corner of opening alpha at that boundary point, then I can control asymptotically the value of the limit of the pseudo-hyperbolic derivative when I approach the point. Here is my curve gamma in, well, by controlling some angle. So in other words, at least for these boundary points, these particular boundary points, the hyperbolic derivatives notice the geometry, not only on the way we are approaching to, but also the geometry, I cannot use the pointer, of the range of the domain, okay? Well, of course, this theorem gives me the Osakawa and Ono result. And indeed, this was sort of the motivation to try to generalize the theorem to that setting. Good. What about non-univalent symbols. It is a beautiful result by due to Haynes that a self-map of the unit disk is a finite Blaschke product if and only if the hyperbolic derivative, in modulus of course, tends to 1 as z goes to the boundary of the unit disk. Okay? But it's also true that there exists necessarily infinity Blaschke products in the so-called little hyperbolic Bloch class, so satisfying this condition here. Indeed, I think he was Wayne Smith who proved this result, who proved that there are some inner functions in this space. But of course, if you apply a Frostman shift to that function, then you can assume that your function is a Blaschke product. And of course, for this Blaschke product, you would have necessarily that the norm of the hyperbolic derivative of the Bloch of this Blaschke product is strictly less than 1. I could say that Alexandrov and Artur studied this type of symbols in terms of symmetric measures, if I remember correctly. Okay, and here I am finally. My favorite, I would say, space, the Bloch space. So now that I presented the pseudo-hyperbolic distance in the unit disk, that behaves that well with self-mappings of the disk, so in the sense that every self-map of the disk is contractive and the automorphisms are the isometries and so on, perhaps I can consider those analytic functions between this metric space and the complex plane endowed with the Euclidean distance. And I will be interested in those functions which are Lipschitz continuous between these two metric spaces. Well, such functions conform the so-called Bloch space. And it is not difficult to check that, well, these are precisely those analytic functions satisfying that this invariant derivative is finite. Okay? The fact that if you give me a composition operator with the symbol phi, it is going to be bounded on the Bloch space follows from, essentially from the Schwarzschild lemma and the closed graph theorem, okay? So this is what I wrote here. So just like in the Hardy space, in that case, it was due to the Littlewood subordination theorem, and in this case, the Schwarzschild lemma. Then we have that every composition operator is bounded on this space. But this space has a very nice property. The property that gives the space the name of conformal invariant. So not only the composition with any automorphism is again in the Bloch space, but also this semi-norm. This is of course not a norm, since it depends on the derivative. This semi-norm is exactly equal to the semi-norm of f. Well, I was saying that this is a semi-norm. Of course, the semi-norm of any constant function is identically 0. But if we consider the Bloch space modulo the constant function, so we identify the functions if they differ only by its value at the origin, then this is a true norm in this quotient space. And indeed, this is a result by Alfonso Montes Rodriguez. It's not difficult to obtain the norm of this operator acting on this quotient space. This is precisely equal to the norm of the hyperbolic derivative. Okay? But what about the norm we usually consider when dealing with the Bloch space? Since this part over here is only a semi-norm, we can add the value of the function at the origin, And in this case, we obtain a true norm in the Bloch space, okay? I always thought, mostly when I was young, that y0 is important, since this space is sort of defined in terms of a hyperbolic distance, and it does not see, it is invariant by automorphisms of the unit disk, but, well, someone told me, well, 0 is the center of the unit disk, so that's true. Well, properties of this Bloch space. It is a Banach space, you know, with this respect to this norm. It is a non-separable space, and well, every function in this space with norm 1, well, I wrote this result here by considering functions with norm 1, but if you just review how you prove it, then you can get the norm involved here if needed. Oh my God, this is difficult to me. Well, you can control, of course, it comes from the very definition of the Bloch space, but also, well, I included here the calculations by using the fundamental theorem of calculus. You can control the Euclidean distance between these two values in terms of the hyperbolic derivative of between the points 0 and z, okay? And, well, equality holds for these logarithmic functions here. You choose lambda suitably so that you can get the modulus here given z, and you get what it is, okay? Well, perhaps what is a bit less known is this result due to Yamashita. It says the following. So just assume that you are analyzing the Bloch semi-norm here, and you name f, the set of points where this function attains a local maximum. And for some reason, the intersection of this set with some hyperbolic geodesic segment, some of these nice curves I draw here, has a cardinal equal to infinity. Then you are done. Your set is the whole geodesic. And your function is essentially one of those logarithmic functions composed perhaps with an automorphism of the unit disk that maps, well, in this case, the diameter to the corresponding geodesic. So somehow, if we want to get equality here, notice that the Bloch semi-norm, well, this is going to be always less than or equal because, well, this is what it is, right? But if I want to have an equality here, then I do need my function to be one of the logarithmic functions I showed you before. Okay, that's the rigidity that bothers me a lot with this problem, as you will see, okay? I mentioned before a result on the isometries of composition operators on the Hardy space. Well, I thought I was not going to need these 50 minutes, so I included here some theorem I also got with Dragan Vukotic on the isometries of the Bloch space among the composition operators. And somehow I decided to include it here because it will give me some intuition on the conditions I have to control in dealing with the calculation of the norm of the composition operators on the Bloch space. So here are the symbols that induced isometric composition operators on the true real space, but somehow this is fake because any symbol inducing an isometric composition operator has to fix the origin. And therefore, if it fixes the origin, what I'm getting is that the semi-norm has to be preserved if I want to get that condition on the preservation of the norms. So the thing is that if you have an isometric composition operator in the Bloch space, then the symbol is either a rotation, or it has this funny property. It fixes the origin, and for any point you get in the unit disk, you can find a sequence of points that don't necessarily go to the boundary, such that at the same time, phi of Zn approaches A, and the modulus of the hyperbolic derivative at these points approaches in modulus, I already said modulus, approaches to 1. This is a sort of funny property, and well, the proof of this result is not difficult, but what was nicer for us is to find a function satisfying this condition here that can be described in a sort of easy way. And here you have an example. Any thin Blaschke product that fixes the origin induces an isometric composition operator in the Bloch space. And a thin Blaschke product, well, you probably know, so the zeros are set n, and we ask these zeros to satisfy this condition here, okay? Notice that such Blaschke product, and indeed such function phi, will have Bloch norm equal to 1. I have to mention at this point a result due to Colonna, Flavia Colonna, who also characterizes the isometries among the composition operators on the Bloch space. And her characterization was given in the following terms. C phi is an isometry on this space if and if and only if phi fixes the origin and its Bloch seminorm is equal to 1. I can prove that this condition implies hers, but I don't know how to prove the converse directly, at least. After all these years, I am not able to prove it, but this is it. So how to prove this theorem? Well, let's start by proving that the symbol must fix the origin if we want to get an isometry. In this case, you write, well, this is the norm of f. This has to be the norm of f composed with phi. This is what is written here. But the semi-norm of this composition is always less than or equal to that the semi-norm of phi, and therefore the semi-norm of phi is equal to the norm of phi minus the value at the origin. And now you choose your favorite Bloch functions. Namely, on this occasion, these are the automorphisms of the unit disk. This must hold for any automorphism of the unit disk. If I get the one which maps phi of 0 to 0, then I directly have my result, okay? So this proves that phi must fix the origin, and once I know, I mentioned that before, that phi fixes the origin, then I am almost done, because I just work with the semi-norms. Okay? And here is what I do. I repeat that I decided to include this here. This is easy. I mean, this is just multiply, divide by the quantity you may need, and triangle inequality or supremum of the product, or blah, blah. But notice that this is essentially what we are doing. If I consider, again, these automorphisms of the unit disk, then here is the semi-norm I am considering, multiply and divide out by this quantity here. And well, since I'm dealing with an automorphism of the disk, then this product coincides with the quantity I wrote here. And this is what I get. Something less than or equal to 1, something less than or equal to 1 is equal to 1, and therefore this condition must hold. So here is the proof. Okay? But please bear in mind these calculations here. I multiply and divide out by this quantity so that the hyperbolic derivative is involved in my calculations. Okay? And this is precisely what Dragan and I made to get these estimates for the norm of a composition operator on the Bloch space. The lower one is obtained just by using the Bloch function 1 and the Bloch functions f lambda, those logarithmic functions I showed you before. Of course, all these functions I just mentioned have Bloch norm 1, and therefore the norm of C phi is greater than or equal to the norm of these functions composed with phi. So this is what I am writing here. This is precisely the norm of f lambda composed with phi. Then if I take the supremum over all lambda of modulus 1, then I get this lower bound, and as I said, the function 1 gives me the 1. And in relation to the upper bound, we essentially argue as before, okay? We essentially argue as before. But a direct consequence is the following. Notice that whenever this quantity here, which is stated in geometric terms, just geometric terms, is less than or equal to 1, then the norm of our operator is equal to 1. Okay? And as long as this quantity here is strictly greater than 1, sorry, this is a misprint, greater than 1. This is the interesting case. And I can sort of align the values of phi of 0 and this sort of marvelous value of phi of b, where that b is related to the point where the supremum of the hyperbolic derivative is attained. I draw it inside the disk, just assuming that this happens inside the disk, but of course that could be a point on the boundary of the disk. If these two values are aligned, so they belong to the same diameter, the norm of the composition operator is precisely given by this quantity here. I'm not proving this. I had written this just to show you the proof on the blackboard, but essentially what you have to do is, again, multiply, divide by 1 minus something appropriate, and that's it, okay? And this question about the alignedness, notice that it follows from this value here. So whenever I consider the logarithmic function, its derivative gives me this lambda here. So if I want to get the hyperbolic derivative, I need to put the modulus here. But if I put the modulus here, I also need to control the lambda so that the modulus can you see? Sorry, perhaps, well, but I think it is clear. So somehow this can be controlled as long as these two values are collinear. And well, just to say something as a corollary of this result, of course, well, I mentioned before that a finite Blaschke product was characterized by Heinz as those analytics of mappings of the unit disk such that the limit to the boundary, the whole boundary of the hyperbolic derivative is equal to 1. So that this value phi of b, where b is the point where the hyperbolic derivative, the supremum, is attained, is going to be any of the boundary points on the unit circle. And therefore, this is going to be aligned with my value phi of 0, and therefore I have the exact norm. This is what it is. Again, if I can control well, what is the relation between the values of phi of 0 and, well, the value where my self-map has an angular derivative, then I'm also done. So again, this is a consequence of the fact that here I am assuming that I can align these two values. And to finish, just to, well, to get a sort of analogous result for the norm of affine transformations in relation to their result, I'm done. On the Hardy space, we can compute the norm of a composition operator induced by these affine transformations. Notice that in principle here, this condition about the alignment of the values is not satisfied necessarily, but the point is that, well, I can assume without loss of generality by using rotations from inside and from outside that these A and B are real positive numbers. And that gives me that condition that the points I need to control are on the same diameter. And under this assumption, this is just a calculation, but it gives me essentially what I have written here. So the norm of the composition operator induced by this particular class of affine symbols is controlled. Well, here in trying to control the exact norm of a composition operator in the Bloch space, well, we obtained these results I'm showing in this last slide. So, well, we can prove that whenever the phi of D is compactly contained in the unit disk, then there is a function f of norm 1 such that the norm of the composition operator acting on that function is precisely equal to the norm. And indeed, we can tell you that as long as an extremal function for the norm of C phi exists, then, well, if the function, if the norm of the operator is strictly greater than 1, the sort of difficult case, then the function must fix the origin. Of course, if the norm is 1, then the function 1 is extremal for the norm. And moreover, these extremal functions, in the cases they exist, well, they satisfy this funny property that somehow allows us to consider sort of compactly contained symbols. Okay, but, well, so far we cannot tell you more. So thank you very much for your attention.